Welcome back. Now, in this lecture, we will solve two numericals using a Kenlayer software and understand how the vertical stress on the subgrade is influenced by the thickness above the subgrade layer. So, we will move to the numerical here. The first one is using a two-layered system with a single wheel. So, first let us understand the problem here. You have a circular load having a radius of 152 millimeter. Let us focus here SI system of units. So, circular load having a radius of 152 millimeter and a uniform pressure of 552 kilopascal is applied on a two-layered system. So, you have a two-layered system here. The subgrade has a elastic modulus of 35 megapascal and it can support a maximum vertical stress of 55 kilopascal. So, the catch here is the stress on the subgrade is limited to 55 kilopascal, it cannot exceed beyond that. If HMA has an elastic modulus of 3.45 gigapascal, what is the required thickness of full depth pavement? This is the first part of the questions. So, above a subgrade, you have a HMA layer. So, HMA layer has a modulus of 3.45 gigapascal. Now, what is the thickness of a top layer required? So, now in the next part of the questions, you have if the thin surface treatment is applied on a granular base with the elastic modulus of 173 megapascal, what is the thickness of base course required? So, the question is like you have a subgrade layer, above a subgrade, instead of a hot mix asphalt layer, you have a base layer and the base layer is a granular layer. So, the modulus of this base layer is 173 megapascal. Now, you have a difference here. If you use HMA, the modulus is going to be 3.45 gigapascal. This is 173 megapascal, which is much less than the HMA layer. So, above a base layer, you have a thin HMA surface. So, this is the structure here. Now, what is the thickness of a base course required? See, if the surface is too thin, we do not consider it as a structural layer. So, the top surface is not considered as a structural layer. So, again you can do an analysis assuming that this is also a two-layered system. So, first we will see this one. So, you can go to Kenpay, open a Kenpay software and go to layer input and start with a new file here. So, open a layer input in a Kenpay, start with a new file. When you give a new file, you will be named as an untitled. So, you will get something like an untitled. Open a general input. So, these are the general inputs you have to define. So, first give title, type of material is linear, no damage analysis, number of period we are going to use only one because you have only one modulus, number of load group it is going to be single axial, single wheel as per numerical. You know what is number of integrations, tolerance for integrations and number of layer, it is a two-layered system, okay, and number of Z coordinate, it is only one and we need it exactly at the top of a subgrade layer. Maximum cycle of numerical integration, leave it as a default value. Now, everything is default, only thing is you just go and change the system of unit to SI and click OK. So, once the general input is done, now next is Z coordinate. So, this is a thickness here, this is our layer. Now, where exactly you need to determine stresses and strain is at this point. So, this is a point we need to determine stresses and strain. So, we need to give Z coordinate to be this, that is distance from the top to this point. So, it is a thickness. See, we need a thickness of a top layer, but that is what we need to determine. We will do it based on the trial and error basis. So, we will assume the thickness and find out what is the stresses here and we will check whether that is within the allowable limit. So, let us assume to be 13 centimeters. So, I will assume the thickness to be 13 centimeters or if you give it in millimeter 130 millimeter. So, your Z coordinate you have to give it as 13 centimeters. So, if you do that your Z coordinate input is done. Next one is a layer input. So layer input, you need to define a structure here. Thickness of first layer is 13 centimeters. Second layer is infinite, you cannot change anything. Poisson's ratio, let us assume the Poisson's ratio to be 0.5, 0.5. If you want, you can go change the Poisson's ratio of an asphalt layer to be 0.35 and try also. But as of now, I will keep the Poisson's ratio to be 0.5 and 0.5. So once this is done, next input is a moduli input. So when you click a moduli, you will get one period. When you click on this, you will have two layers, because we have defined only two layers, modulus of each layer to be given here. So as per our numerical, modulus of a first layer is 3.45 gigapascal, and modulus of a soil layer is 35 megapascal. So you have to convert into kilopascal and give here. So once you do this, the modulus input is done. Now next is load. So load here, it is a single axial single wheel. So we assign 0 for defining single axial single wheel. So the contact radius is 152 millimeter. Contact pressure is 552 kilopascal as per numericals. We don't have W, YW and XW here. This is because it is a single axial single wheel. So once this input is given, now you need to give where exactly you need a stress, whether you need it at the center of loading or at the periphery of loading. So it is a critical stress what we are interested in, and you have also in a numerical, it is given that exactly at the center of loading. So we will give only one point, and you just double click on this, you will get this window here. In this window, you can define an RC here. RC is exactly at the center, so it is 0. So, by defining these 5 parameters, our input for load is done. So, once you complete all the informations, all the input in the layer input category, you can just go save as. You can save it using any file name and then come out of a layer input by clicking exit. So, after you give all the input, you can compile using a Kenlayer button. And when you compile using a Kenlayer button, this is what you will see here. And the results I have given here in the tabular column, you can see that in the results you have radial coordinates. We have given radial coordinates to be 0. So you have radial coordinates and vertical coordinates. So you have vertical coordinates. If you give 2 vertical coordinates, you will have 2 points. If you give I have given 2, so that's why you have 2 points here. One is at the surface, another is at the interface of 2 layers. So vertical displacement, vertical stress and strain. So you have vertical stress and strain, radial stress and strain, tangential stress and strain, and shear stress and strain. So the negative sign indicates the tensile nature and the positive sign indicates the compression nature. So what exactly we need? Stress on the top of a subgrade layer. So it is exactly at 0.13 centimeter below the surface layer, and we need to find out what is the vertical stress. So this is a vertical stress at the top of a subgrade layer, 58.509 kilopascal. So our constraint here is we need to restrict the stress on the subgrade layer, top of a subgrade layer, to be 55 kilopascal. And this is what our need is. So, as per our analysis, we have 58.509. So, this clearly says that stress is more than the allowable value. So, this thickness 130 millimeter above the subgrade layer is not sufficient to restrict the stress above the subgrade layer to 55 kilopascal. So this is not sufficient. Now what you can do is you can increase the thickness to 135 millimeter and proceed in the same way what you did it, and you can check what is the stress above this, and this is a result for 135 millimeter. So you can see that the stress above the subgrade layer is 54.965 kilopascal, which is well within the allowable stress of 55 kilopascal. So you need minimum of 135 millimeter to restrict the stress on the subgrade layer to be within 55 kilopascal. This is what the numerical says. So, when you increase the top layer thickness, the stresses and strain on the subgrade layer will be reduced. So, the second part of a numerical, in the second part of a numerical, so instead of a surface layer, if we use a base layer 173 megapascal, then what is the thickness of a base course? So, as the modulus is less compared to the previous problem, so we will try and change the parameters. So, what are the parameters you need to change is, one is the modulus value. So, the modulus value is, the first layer modulus is 173 megapascal and the modulus of second layer is same as the 35 megapascal. So, one input which you need to change is a modulus. So, and you need to find out stresses and strain exactly at the layer interface. So, if you are going to vary the thickness, the location is also going to vary. Let us assume some number and find it out. Now, I will assume it to be 38.5 centimeters. This is based on a trial and error. You can just increase the thickness and find out at what exact thickness you get the allowable stress value. So, I am going to use here 38.5 centimeter. So, thickness of the layer, first layer is going to be 38.5 centimeter, thickness of second layer is infinite, you cannot change it, Poisson's ratio is 0.5 and 0.5. Now, if you change this input from the previous case, this is what the result you get it. What we are interested in is, at the center of loading and at a depth of 38.5 centimeters, what is the vertical stress at the top of a subgrade. So, at the top of a subgrade, a critical vertical stress, as per, if you provide 38.5 centimeter is 54.613. So, you have a stress well within an allowable limit, that is 55 kilopascal. So, you need a minimum thickness of 38.5 centimeters. So, if you provide a granular base, your thickness requirement is 38.5 centimeter. If you provide a asphalt layer or a HMA layer that has a higher modulus, you need a thickness of 135 millimeter or 13.5 centimeters. So, this again the values, thickness values varies with the modulus. So, if you increase the thickness, you can reduce the stresses and strain on the subgrade layer. So, the next problem what we will look into is a two-layered system, but instead of a single wheel load, we will use a single axial dual wheel. So, we are going to use a dual wheel here to find out stresses and strains. So, let us understand the problem here. You have a two-layer system and it is subjected to a dual tires and each have a contact radius of 115 millimeter and a contact pressure of 583 kilopascal. The center to center spacing between the dual wheel load is 343 millimeter. Layer 1 has a thickness of 152 millimeter and has a modulus of 690 megapascal. Layer 2 has an elastic modulus of 69 megapascal. Now, determine the vertical deflection at a point A. So, the A is at a depth of 6 inch, that is 152 millimeter and it is beneath the center of one loading area. So, when you sketch the plan of a load, it looks like this: circular two loads with the center to center spacing of each load. This is 343 millimeter and you need exactly at this point what is a vertical deflection here. This is a point A in plan, this is a point A in elevation. So, now let us see how to give the input. See, all input here remains the same and the only difference here what from the previous problem is we are going to use dual wheels and change all the numbers as per this problem. Now we will see only the dual wheel input here. So you need to assign one for dual wheel. The contact radius is 11.5 centimeter. Contact pressure is 483 kilopascal. So you need to define W, that is YW, which is nothing but center to center spacing between two wheels. So that is 34.3 centimeters. XW, you don't have another axial here, so you keep XW to be 0. Number of radial points, if you give 1 and double click on this, you don't get RC here like in a previous case. You have XPT and YPT. So this X coordinate and Y coordinate. Y coordinate is defined along this direction and X coordinate is defined along the movement directions. So this point is exactly where X is 0, Y is 0. So you have X 0 and Y 0. So once you give all this input and compile it, this is the result you will get it. See, what is that we need? At a vertical distance of 15.2, that is at the interface between two layers, your vertical displacement is what you need to find out. The vertical displacement is 0.06735 centimeters. This is what our vertical displacement is. Now you can also check by changing the z coordinates, this is this value, and check where the vertical displacement is critical. So in this lecture, we were focusing on a two-layered system and we used a Kenlayer software to determine vertical stress and deflection at the top of a subgrade layer, and we have seen that the modulus of a top layer influences the stresses at the subgrade layer. So in the next lecture, we will focus on the tensile strain and we will see how the axial configuration influences the tensile strain at the interface of a two layer. Thank you so much and we'll come back.